Welcome to the fifth lecture of module 4. We are discussing absorption. In the previous lecture, we have mainly considered two things. One is packed tower design, for dilute gases. And second thing, we have discussed packed tower design for concentrated So, for dilute solutions, we generally consider the mole fractions of the solute both in gas as well as liquid phases should be less than 0.1, that is 10%, and above that we should consider concentrated solution. So, these two methods we have discussed and we have seen the examples how to solve different problems. In this lecture, we will discuss the correlations, some of the important correlations for mass transfer coefficient. Mass transfer coefficients. And second thing we will discuss HETP concept, that is height equivalent to a theoretical plate. HETP concept. So, let us consider the first thing, correlations for mass transfer coefficients. The mass transfer coefficient, that is MTC, mass transfer coefficients in packed towers generally usually expressed in the following terms. What are those? Serud number. SH, and secondly the Coulomb factor, which is defined as JD, the height of transfer unit. Height of transfer unit, which is HTG or HTL. The mass transfer coefficients generally kg, small kg, KL, etc. mainly depends on the gas flow rate second the liquid flow rate, and third the physicochemical properties. Physicochemical properties, that is fluid properties, and transport properties. So, the fluid properties like for example, density, viscosity, etc., and the transport properties like physical solubility, molecular diffusivity, etc. So, there are several correlations available in the literature, which are derived mainly from the experimental data for different systems. So, some of the important equations we will discuss here. So, very simple equations, One is for gas phase mass transfer in packed bed. Gas phase mass transfer in packed bed. Here the packing used is racing ring or barrel saddle, and Sulman and co-workers, in 1955 proposed the following equations: J d is equal to 1.195 ds g dash divided by mu g 1 minus mu L whole to the power minus 0.36. ds is the diameter of sphere, ds is the diameter of the sphere having the same surface area, of a piece of vacuum particle. And mu g is the gas viscosity, mu L is the liquid viscosity, and G dash is the mass flow rate of the gas. G dash, this is the mass flow rate of the gas. Let us consider another system, absorption of SO2. In water in a packed bed. The packing used is 1 inch racing ring, and there is a correlations which is given by Datta 2007 . Following correlation. HTG is equal to 1.24 G dash to the power 0.3 divided by L dash to the power 0.25 feet, and HTL is equal to 0.37 divided by L dash to the power 0.18 feet, where G dash and L dash gas and liquid flow rates, gas and liquid flow rates in pound per hour feet square. So, another correlation which is given by Unda and co-workers in 1968 for the mass transfer parameters. A effective divided by AP is equal to 1 minus exponential 1.45 sigma C by sigma to the power 0.75 Reynolds number to the power 0.1, Prout number to the power minus 0.05 and Weber number to the power 0.2. So, each number we will discuss later, and KL into rho L divided by mu L into G to the power 1/3 is equal to 0.0051 Reynolds number to the power 2/3 A p by A effective to the power 2/3 a Schmidt number to the power minus half A p T p to the power 0.4. Another correlations for K c divided by A p d g is equal to C is a constant, R e g to the power 0.7 Schmidt number to the power 1/3 A p d p to the power minus 2. So, here this C is equal to 2.0 for d p less than 15 millimeter and this equal to 5.223 for d p greater than 15 millimeter. D p is the nominal packing size, sigma c is the critical surface tension at the packing surface. Critical surface tension at the packing surface in dynes per centimeter, and it varies like for ceramic it is 61, polyethylene 33, glass 73 and metal 75. R e g is equal to mu g rho g by A p mu g. Schmidt number is equal to mu g by rho g into d g. R e L is equal to mu L rho L divided by A p by mu L. This is G, this is equal to U L square A p divided by G. Weber number is equal to Weber number which is equal to U L square rho L by sigma L A p. So, here K c and K L which is the mass transfer coefficients rho L is the density, mu L is the viscosity, d is the diffusivity, meter square per second, A effective is the effective gas liquid specific interfacial area of contact, and A is the specific surface area of dry packing. Specific surface area of dry packing, say meter square per meter cube, and u is the superficial velocity. Now, let us take a very simple examples how to calculate the height of transfer units Hg and HL. So, if we take the example, sulfur dioxide is to be absorbed by water from a dilute gas stream in air using a pack tower at 30 degree centigrade and 1 atmosphere pressure. 1 inch racing rings is used as packing. The liquid flow rate is 3000 pound per hour feet square and the gas flow rate is 400 pound per hour feet square. Predict Hg and HL. So, if we go back and look into the correlations given for Hg and HL, which is for 1 inch racing ring and absorption of sulfur dioxide, Hg equation is given and it is given that liquid and gas flow rate. So, if we write these equations, Hg is equal to 1.24 G dash to the power 0.3 divided by L dash to the power 0.25, which is equal to 1.24 G dash is 400 pound per hour feet square to the power 0.3 divided by liquid flow rate is 3000 is to the power 0.25, this much feet. So, it is equal to 1.01 feet. HL, which is 0.37 divided by L dash to the power 0.18 feet. So, which is equal to 0.37 divided by 3000 to the power 0.18, which is equal to 0.09 feet. So, similar systems can be solved using these correlations and for other systems as well. So, now we will discuss height equivalent to an equilibrium stage or theoretical plate. The common device for absorption we have discussed before. For absorption, is pack tower and second is tray columns. tray column. This HETP method is a simple design method, for packed towers. Which is developed long before, and this ignores the differences between stage wise and continuous contact. So, HETP is defined as HETP is equal to Z divided by NT. Z is equal to height of packing and NT is equal to number of ideal stage or trays required, number of ideal trays required to do the same job. So, it is the ratio between the height of packing and the number of ideal stage required for a given job. Now, let us consider the following figures. We have two different trays, and this is named as nth tray, this is n plus 1, and say there is a liquid hold off on the tray. So, the liquid which is entering to nth plate is x n minus 1, and which is coming out from this tray is y n, the gas which is coming out, and the liquid which is coming out from this tray towards the down is x n, and the gas which is entering to this plate is y n plus 1, and the gas which is coming to the n plus 1 stage is y n plus 2, and the liquid which is coming out from this is x n plus 1. Now, if we plot the equilibrium curve and the operating line curve, So, this is y n plus 2, this is y n plus 1, this is y n, and corresponding to this is x n, and this is x n plus 2 and this is x n plus 1. So, x and y. So, this is equilibrium line, and this is operating line. So, here we have used two trays, nth tray and n plus 1th tray. Now, if we consider n plus 1 tray and if we do the balance, consider the n plus 1th tray, inlet concentration of gas, into n plus 1th tray is equal to y n plus 2. This is in mole fraction. Outlet concentration of gas from this tray is y n plus 1. Inlet concentration of liquid into n plus 1th tray is equal to x n, and outlet concentration of liquid from this tray is x n plus 1. And let consider G dash, the gas flow rate per unit area, and L dash, liquid flow rate per unit area. So, both assumed constant. Then, if we do the mass balance over n plus 1th tray for n plus 1th plate, so rate of mass transfer is equal to G dash y n plus 2 minus y n minus 1 would be equal to L dash x n plus 1 minus x n, and rate of mass transfer over a packing height of Z would be equal to kg a bar pt Z into y minus y star average, where y minus y star average is equal to average driving force over the packing height of Z. So, then if the rate of mass transfer on a tray is same as the rate of mass transfer over a packing surface, we can write kg a bar pt into Z y minus y star average would be g dash y n plus 2 minus y n plus 1. So, from which Z we can calculate it is g dash y n plus 2 minus y n plus 1 divided by kg a bar pt y minus y star average. It is reasonable to take this y minus y average as a log mean overall gas phase driving force between the point P and Q. So, between this is the operating line. So, between this point P and Q, it is reasonable to take the log mean overall driving force for y minus y star average. So, if we take that y minus y star average would be y minus y star q minus y minus y star p divided by ln y minus y star q divided by y minus y star p. So, this would be y n plus 2 minus y n minus 1 minus y n plus 1 minus y n divided by ln y n plus 2 minus y n plus 1 divided by y n plus 1 minus y n. So, from the figure we can write y n plus 1 minus y n divided by y n plus 2 minus y n plus 1 is equal to y n plus 1 minus y n divided by x n plus 1 minus x n divided by y n plus 2 minus y n plus 1 divided by x n plus 1 minus x n. So, which is equal to slope of the equilibrium line divided by slope of the operating line. So, which is we can write m by L dash by G dash. So, from this we can write m G dash by L dash minus 1 is equal to y n plus 1 minus y n divided by y n plus 2 minus y n plus 1 minus 1. So, which is equal to y n plus 1 minus y n minus y n plus 2 minus y n plus 1 divided by y n plus 2 minus y n plus 1. So, now, we can substitute this in the equations of y minus y star average is equal to m g dash by L dash minus 1 into y n plus 2 minus y n plus 1 divided by ln m g dash divided by L dash. So, therefore, Z would be G dash divided by capital K G A bar P T into ln m G dash by L dash divided by m G dash by L dash minus 1. So, which is equal to H T O G ln m G dash by L dash divided by m G dash by L dash minus 1. Therefore, HETP which is equal to Z, we can write equal to HTOG ln m G dash by L dash divided by m G dash by L dash minus 1, which is we can write HTOG ln of the stripping factor S divided by S minus 1. The equation will not be valid for mg equal to L. This HETP is generally used to characterize the performance of packing. HETP is used to characterize the performance of packing. So, a good packing will have small HETP. This is widely used in packed distillation and it usually varies between 1 to 3 feet. This HETP depends on the following factors. One is the gas and liquid flow rates. Second, the type and size of packing. Physicochemical properties. The equilibrium relations, and the liquid and gas distribution. Liquid and gas distribution. Thank you.